Today, I'm going to be talking about Routh Criterion stability. So, Routh Criterion stability is used to find the stability of a system for third order polynomials and upwards. Now, let's start with the second order. For second order system, to find the poles, if the poles are on the left hand side, it means the system is stable. If the poles are on the right hand side, it means the system is unstable. So, let's find the poles of the system. We're going to equate the denominator to 0. So, this is a quadratic equation. You can find that the root of this equation will be minus 2 and minus 3. If we are to draw that on the plane, this is the imaginary line, this is the real line number. These are negative, so they're going to lie on the left hand side. And so therefore, I tell you that if poles are on the left hand side, means the system is stable. But if they were on the right hand side, the system was going to be unstable. So now let's move on to the third order equation. This is the transfer function of a third order system, and you're told to find the stability of the system. You can find the roots of the denominator when you equate it to 0, but that can get extremely cumbersome for like 10 other polynomials. It can be really big, it can go up to like 20. So how are we going to solve this with root criterion stability? This is the formula. Here we have that where a naught s of n represents the highest order polynomial, which is 3, then 3 minus 1, 2, 2 minus 2 minus, or rather 3 minus 2, 1, and 3 minus 3. Sorry, this is supposed to be 3, which is 0. Now next, a naught, these are coefficients. So a naught is going to represent the coefficient of the first variable here, the first polynomial here, which is S3. And the coefficient is 1. So N is going to be 1. A1 represents the coefficient of the second variable, which is 2. A2 is going to represent the next variable, 1. The coefficient is 1. And A3 is going to represent 3. So we're going to just write this out neatly. S, we start with S raised to the power 3, followed by S raised to the power 2, followed by S raised to the power 1, followed by S raised to the power 0. A naught is 1. Let's draw a line. 2, 1, and 3. So now it's left for us to find B1, C1, B2, C2. Now the root criterion stability method doesn't exactly tell you the roots of the equation, but it tells you how many poles you have on the right hand side of your step transfer function. And to find that, we're going to see if we're going to find any sign change in only the first column. I'll explain that shortly. Now first, let us find B1, the value of B1. B1 is equals to A1, A2, you can see, let me show you here. Whatever you have here, multiply it A1 times A2 minus A0 times A3. So we're going to have 2 times 1 minus 1 times 3 all over A1. What's that? A1? 2. So this is going to be 2 minus 3 over 2, which is equals to minus 1 over 2. So I can replace this B1, since I've gotten it as minus 1 times 2, minus 1 over 2. Let me move this to the side so you can see clearly. Now next, let's find B2. Now B2, as you can see it here, is A1, A1, A4 times A0, A5. Now it can be seen from our table that we got it that we have no values here, so we're going to take them as 0. So we're going to have 2 times 0 minus 1 times 0 all over A1. A1 is 2. This is going to be 0 over 2, which is equals to 0. Now next, before we go to the next step, let's replace B2 with 0. Next, let's find C1. C1 as given in this equation is B1 times A3 minus A1 times B2 all over B1. So let's write that. That will be minus half times 3 minus 2 times 0 all over B1 minus 1 over 2. Once using your calculator, you're going to get 3 as your answer. Let's write 3 here. Now, remember, I told you we're only interested in the first column. So now that we've gotten the first column completely, we can now check for how many poles we have on the right hand side. So how we're going to do that is we're going to check for sign changes. Now, I moved everything so we can see, focus on the first column. Going from this point to this point, there's no sign change. Here's positive, here's still positive. Now moving from this point to this point, you can see here's positive and then here's negative. There's a sign change. So there's one sign change. Now next, when we move to the next line, we see that we go from negative to positive. That's a second sign change. So therefore, in this particular system, we have two sign changes. Therefore, we have two poles that lie on the right hand side of the plane. And I told you, right hand plane, sorry. And I told you if you have any poles lying on the right hand side of your plane, that means the system is unstable. So therefore, this system, since it has two poles lying on the right hand side, this system is therefore unstable. Let us focus on this third example. This is a special case. I'll show you one. So let's write our columns S4, S3, S2, S1, and S0. Our first coefficient is 1, second is 3, third is 3, fourth is 3, the last is 2. Now let's start by finding our V1, V2, and sorry, this is supposed to be C1, sorry. Now B2, C2. Let's start finding our B1. Our B1 is giving us A1, A2, that's this times this, minus A not A3 times this. Let's have 3 times 3 minus 3 times 1 all over A1, which is 3, equals to 2. So I'm going to replace B1 with 2. Next, let's find B2. B2 is giving us A1 times A4, which is A1 times A4, minus A0 times A5. That'll be 3 times 2 minus 1 times 0 all over A1, 3. We're going to have 2 as our answer. Yeah, it's safe to replace B2 with 2. Now next, let's focus on our C1. C1 is B1 times A3 minus A1 times B2. So we're going to have 2 times 3 minus 3 times 2 all over B1, 2. The final value will be 6 minus 6 over 2, which is 0. So let's replace C1 with 0. You can now see that there's a 0 on our first column, the column that is supposed to help us know how many poles are on the right hand side. That's the problem. So what we're going to do is that we're going to replace this 0 with a very small value called epsilon. Epsilon is a very small positive integer. Now let's find C2. C2 is going to be equals to B1, right? B1 times A5 minus minus a1 times, sorry, a1 times b3. So we're going to have 2 times 0 minus 3 times 0 all over b1, 2. It's going to give us 0 as well. So we can place C2 with 0. It doesn't matter if C2 is 0 because we only focus on the first column, not on the second column. So now let's find D1, because we are finding D1 because C1 was 0. So you need to go to the next line. Now to find D1, we're going to use the same pattern we've been using. It's going to be A times 2 minus 2 times 0. We're going to have 2 times epsilon minus 2 times 0 over epsilon. It's going to come out as 2 epsilon over epsilon, cancel out, giving us with 2. So now, to check for sign changes in the first column. Now let's look at the first column. Look at the values before and after epsilon. So starting from here, because no sign change. Let me move this aside so that we can concentrate on the first row. This is positive, this is still positive, no sign change. Next move from right here, no sign change. Let's move from here to here. This is epsilon is a very small positive number. Let's move from here to here. It's still positive. So we can see there's clearly no sign change. Now, well, I told you before that no sign change means opposite on the right hand side, right? But in the case where you have replaced a value with epsilon, that's a very small positive integer, the system cannot be stable. It can only be marginally stable. So therefore, this system that we just treated right now is a marginally stable system. So thank you for listening. I hope you understand. Don't hesitate to leave your questions in the comment section. Thank you.